Hello. The topic for this lesson is least squares problems. So let's begin with a brief overview of the lesson. So let's consider the system of equations ax equal to b, where a is given over here and b is given as well. So a is a matrix, b is a vector, and if we give this system to linear solve to solve, then linear solve kind of complains that this system has no solution. So the system is inconsistent. Now, in such cases, we can use the method of least squares to find an approximate solution for a system. And we have a function called least squares. We'll do that for you. So here is the answer. The answer is 6.17 and 5.9 for the two variables in the system. The question is, what happened over here? Well, here's a plot that shows what happened. We had a system of three equations. There were three straight lines. Those three straight lines did not meet in a point, so there is no solution, as linear solve says. But there is a kind of approximate solution, which is the red dot over here, which gets as close to all three lines as possible, but is not really a solution. So that's the idea of least squares. You want something that's like a solution, but not quite a solution. Okay, so let's make a formal statement about the least squares problem. So let's say you're an m by n matrix A and a vector B. Then the least squares problem is to find a vector x which makes the norm of ax minus b as small as possible. So of course, if you can make it 0, then you really do have a solution. And the question is, why the name least squares? Well, that refers to the fact that this over here is the square root of a sum of squares. Now, the fact is that if you have a least square solution and then you take any other vector, then the kind of error over here is going to be at most the error over there. So you always have a kind of minimal error coming out of the least squares solution. In the picture shown over here, you have the vector b, you have the least square solution, and you can see that the distance over here is less than equal to the distance over there, the norm. Okay, so question is, how do you solve these least squares problem? Well, there are several ways. So the first way, which is quite popular if you do, let's say, do statistics, is to use the so-called normal equations. So you do A transpose times A of x equal to A transpose times B. And so for example, over here you have the same equation as early on, Ax equal to B, and I can do a linear solve for this system of normal equations. So you have A transpose dot A, etc. And you get back a solution which is the same as that obtained early on. So one way to solve least squares problems is to use the normal equations. But there's yet another way, and that is, if you can assume that the columns of A are linearly independent, then you can actually invert the matrix A transpose A and get a very nice closed form over here. So with the same example for A and B, let's check that you actually have linear independent columns. You see a linear independent over here. And then you can apply this formula over here. So you can do the inverse of A transpose times A and then A transpose times B, and then you get back a solution which is just the same as the solution early on. Okay, there's a third way of approaching it, and that's to use the QR decomposition. So once again, assume that the columns of A are linearly independent and that you have a QR factorization, which we talked about in the last lesson for the matrix. Now, of course, this matrix is rectangular, but it does exist in this case. Okay, now if you can do that and find a QR decomposition, then you can reduce the normal equation or whatever to a very simple system over here. It's an upper triangular system, and that system is R times X equal to Q transpose times B, and that is, of course, a very simple system to solve. So here is the procedure for the same set of equations. You got A and B. Find the QR decomposition, the QR factorization, find Q, find the upper triangular matrix R, that's upper triangular, and then use the procedure over here with linear solve to find the least squares solution. and you see you get back just the same result as earlier on. So I've shown you several ways of doing the least squares solution, but the question is, what's the preferred method? Well, I would recommend that in fact you should use the least squares function in the Wolfram language. So once again, you have a matrix A and a vector B. Then least squares function will actually give you the least squares solution quite easily. So as we actually saw at the beginning of the lesson, you got A and B over here. You do least squares A comma B, and you get back exactly the same solution as earlier on. So least squares function is perhaps the way to go if you really want to find a least squares solution quite efficiently. Okay, now like I said earlier on, the nice thing about the least squares solution is that if you have a least squares solution, then this over here is the least squares error, and that's going to be as small as possible. So in a sense, the least squares solution gives you the best possible approximation to a solution of a given linear system. And of course, if you actually have a solution, then you might get a 0 over here. Okay, so as an example of the least square error, let's again take the same example as earlier on. So now do the least squares solution, work out the error, and compare it with any other vector x, and you see that the error instantly goes up. So you do have a kind of best possible approximation to a linear system when you use the least squares method. And just to point out that really this is all quite useful in practice, let's talk about least squares fitting. So here is a set of data. What I've done is to take a quadratic function, like over here, it's called an x square over here, and then I've added some noise to it over here. So if you plot it, it looks almost like a parabola, but in fact there's some noise over here, which is like what would happen in the real world. Now, given such data, what you can do is you can construct a linear system for doing a least squares fit. So you can use something called a design matrix, which accounts for the fact that you're trying to do a quadratic fit over here. You can work out the vector B, find the least squares solution. Now that's the solution for the coefficients of the quadratic. So here you do a plot, and you see that in fact you got a very nice fit for the data using a least squares method. The least squares method lies at the very heart of lots of practical methods for curve fitting. Okay, so that's the end of this lesson, and the main point is that the least squares method provides approximate solutions for inconsistent linear systems. And we have a nice function called least squares in Wolfram language, which will do this automatically for you. And of course, the main point for applications that they give a powerful technique for fitting curves to data in many fields. So least squares methods are a wonderful way to fit curves in the real world. So that's the end of this lesson, and next time we'll talk about the diagonalization of symmetric matrices, but I'll stop here for now. Thank you very much.